Hello everyone. Again, today the fourth lecture of my short course, and today we're going to proceed with radiation detectors and have today two specific topics: how to detect two types of radiation: gamma rays and neutrons. And the main thing which we care about gamma rays is the topic which is called gamma spectrometry. This is the idea where you should to detect, identify, and quantify gamma emitter. Why it's so important? For example, in some applications, you have just an isotope and don't know exactly what kind of isotope it is. And the task of a physicist to identify it by measuring different gamma lines. That's I would like to present you today how to do it and why we get different energy spectra, and try from them understand the types of isotopes and why this spectra looks in this way. And to understand this, we have to come back to our first lecture, where we were discussing three processes which happen in matter when gamma rays interact with materials. The first process is photoelectric absorption. This is photoeffect process, in other words, and the main idea that electron is ejected from the electron from an atom, and the energy of it's a little bit unclear, specifically from the backgrounds, but I'll try to explain. This is a photon or a gamma ray which interacts with an atom and ejects an electron from the material. And all energy of this gamma ray goes to this electron. And this electron can ionize matter, the material. And in this case, you will get this clean peak, which really corresponds exactly to the energy of gamma ray. The second process is quantum scattering, where you have an electron, an orbit electron, and gamma ray also scatters of this electron is at rest. You will have a distribution of energies between this electron and the scattered gamma ray. And here you can see the spectrum, which usually we get in detectors. This in X, this is like this, also intensity, there, number of counts, and here in X you have an energy, an initial energy of gamma ray. Here you can see this quantum, so-called quantum continuum, which happens when you have different angles of scattering. There are a lot of whole distribution of angles, and every time you get different angle after the scattering. That is why you have this distribution, and it happens. I showed you the formula in my previous lectures, that there is some maximum of energy that can be transferred to this electron, which uses ionization. And the maximum of this energy is called Compton edge. And this Compton edge is located somewhere here and corresponds to the angle of scattering, which is equal to 180 degrees. We are located here. And the third process which can happen is pair production. And here, all energy goes to an electron and positron, and we have this peak, and the energy of this peak corresponds to this value, which really is equal to the energy of gamma ray minus 2 masses of electrons, which is equal to 1.42 MeV. I mentioned it in my previous lecture. So we have all these three processes, and we have to get the real spectrum in our detector, and get the so-called energy resolution. This is peak, which I described in my previous slides. For example, this one, you can see that this peak should be a delta function, a discrete monoenergetic peak. But in reality, we get something like this or something like this. I explained it in my previous lecture, but I'd like to remind you again about this thing, which is called energy resolution. Energy resolution, this is 2.35 sigma divided by an average value, this Gaussian distribution. And if we have good energy resolution, we have this rather sharp peak. If we have a bad or poor energy resolution, we have the peak which is wider. And I will show you later why it's so important. And there are some factors which really define you the energy resolution, which is called the statistical limit of energy resolution. I'm not going to deep into details, just want you to show that in this distribution we can get this value, and we in our detectors count number of, for example, electrons, or number of electron ion pairs, or number of electron poles. Yes. And in my next slides, I will tell you that the best detectors for measuring gamma rays are semiconductor detectors, germanium detectors, and the main reason is that if you look at this formula, you have this n number, which is located here, and this is number of these charge carriers. Remember from my previous lecture that number of charge carriers is equal to the energy of initial energy of the particle and the W value, which is the energy to create one electron ion or electron hole pair. And for example, for ionization chambers, which utilize, for example, argon, this value is 26, and for germanium, this value is about 3 electron volts. That is why this this energy resolution is better for germanium and also semiconductor detectors, because we have more charge carriers. This is for some statistics. So let's back to our exercise with gamma spectroscopy, specifically with scintillation detectors. In order to understand what we get in the detector and what we can expect to see, we can look at this simple picture. This is scintillation detector, and now we are considering different options which we can use. For example, we can have a very small detector, yeah, and as you know, the size of the material, the volume of material strongly depends and defines your ability to detect ionizing radiations. The same thing for gamma rays. You have some assumption that you have a small detector. What processes can happen in this detector? Of course, there can be photoelectric effect, and in this case, if it happens and your gamma ray is fully absorbed, it goes through the photoelectric effect, you will get this peak, which is called photo peak or full energy peak. This is the ideal case, the best case scenario. If you convert immediately your gamma ray into electron, you immediately get this clean photo peak. That's what we are looking for. And all events which are concerning photon scattering, they are not so good for us because they don't contribute to this peak and make our energy resolution worse than it would be. And in this case, for example, there are some process, for example, if the detector size is not very big, your gamma ray is scattered and escapes from the detector. And energy which is deposited exactly in the detector is lower than it's in reality. And you have this picture of the photon scattering. If we have the energy of one gamma ray is more than 1 MeV, remember electron positron pair reduction is a threshold process, and in this case we have a possibility to create this so-called ionization photons. I told you about this reaction when you have an electron and a positron, and then they meet each other, they annihilate and create two photons with energy 4.5 MeV. So in this case, you will have the same picture like this, but you will see this peak which happens here. This peak is called double escape peak, and this peak appears on this picture because two gamma rays are escaping from your detector, and you lose this energy information. The ideal case, if you have very big detector and all processes which I just explained, they happen inside the detector, photoelectric effect, quantum scattering, and all this interaction finally will lead to the photoelectric absorption, and you will get this full energy peak, which really a goal, and of course we would like to have this feature, but in reality it's impossible because we can't, for some applications, can't have these enormous detectors, and we have to use detectors of intermediate size, and the picture will be very similar to the first one, but compared to small detectors, we can get picture, for example, like this, where you have a Compton continuum, full energy peak, and also some events due to so-called multiple Compton events. And these events happen when, remember, this is a stochastic process. For example, one gamma ray can immediately be absorbed, through photo effect. But at the same time, there is a high probability, for example, to have a Compton scattering. In this case, your gamma ray scatters and can go from the detector, or it can scatter again, for example. And in this case, you will have this multiple Compton continuum. In some cases, you also can have, for example, double escape peak when two gamma rays escape from your detector, and you can have a single escape peak. Then only one from annihilation X-rays escape from the detector as well. And here the full energy peak. And in reality, we have, and this picture also, of course, is applicable only for gamma rays with energy more than 1 MeV in order to create positron electron pairs. In reality, in our experiments, we have in gamma ray spectroscopy, we have pictures like this, or like this, but in reality, this is an ideal picture. There are some other effects which can happen in the detector, because the detector usually surrounded by some sort of materials, for example, shielding, and there can happen, for example, such events like backscattering. This is the process when the gamma ray can scatter from the surrounding materials and come back to the detector. And in this case, if you look at this picture, there is it happens that for energy range, for angle range from about 100 degree to 180 degree, you always have the same energy. And if it happens in this manner, you will get this peak, which is usually located here and is equal to 0.2 MeV or less. Some other materials, this process can happen in surrounding materials, and you get this annihilation peak from this electron-positron annihilation process. You can have, for example, X-ray peaks from photoelectric absorption in surrounding materials, which leads to characteristic X-rays, and so on. In real life, your picture is usually more complicated, looking like this compared to this dashed line ideal picture. So why we so care about this gamma ray spectroscopy? Because in some, and specifically energy resolution, because in some applications or some isotopes have the gamma ray peaks which are located very close to each other. And if you look at this picture, here you can see two types of detectors. First one is germanium detector. Here's the spectrum which we get using the germanium detector, and the second one using a sodium iodide scintillation detector. You can see the difference that in sodium iodide you have placed 1, 2, 3, something like that, or 4 peaks, and these peaks, of course, are attributed to some gamma ray photopeaks, and the problem is that the energy resolution of this detector is not good. And all these peaks are summing up, and you can get different gamma ray lights compared to this picture. For example, with germanium detectors, we can see here that it's not clear, but this figures the energies of gamma rays. And you can see that the germanium detector allows you to see different lines, and it's very important to identify the isotope. Here the picture just like to show you how the germanium detector looks like. Usually we rate them at liquid nitrogen temperature in order to decrease the noise, which is caused by thermionic emission. And the device is located, is connected to this diode, which is filled with liquid nitrogen. And process and work with detectors quite complicated compared to scintillation detectors, because if you want to get these nice pictures, you have to keep with detection at low temperature all the time. Just more slides to show you the importance of energy resolution, and you can compare some experimental spectra which were obtained with different types of detectors. Here you can see this in blue lines picture obtained with again germanium detectors, and you can see clear peaks, and each peak corresponds to a unique gamma energy of an isotope. In red, you can see peaks from non-bronze scintillation detector, which has the best energy resolution among all scintillator detectors, but it can be competitive with germanium detectors. You can see some peaks as well. And if you look at sodium iodide detector, you will see that these peaks are wider. And if you have isotopes which have gamma ray energies which are located close to each other, it would be impossible to distinguish between them. Here, just single picture. This is scintillation detector, germanium detector, and proportional counter detector in green. And you can see that germanium detector can be distinguished to very close gamma or X-ray lines, and so it allows you to identify the isotope. And it would be possible with the other type of detector, it will lose the information. And some there are lots of practical applications, and I'd just like to give one example why we should care about this energy resolution, and why we use germanium detectors. For example, there are some issues connected to safety of nuclear materials, specifically nuclear non-proliferation and safeguards. And there are some techniques to prevent illicit trafficking of nuclear materials, specifically from the reprocessing plants. And it can be done with gamma ray spectroscopy. If you compare this spectrum, and uranium has characteristics, gamma lines, X-ray lines at this energies about 100 and 125 keV, and the content of uranium, light enriched, low enriched uranium, which is usually used in conventional nuclear power plants, and high energy, highly enriched uranium, which is used in some specific task, and actually right now is prohibited in many countries and in many applications, as it can be used, for example, for military purposes. And this thing allows you, by measuring this ratio of these X-rays, to distinguish between low enriched uranium and high enriched uranium. It can be done with high purity germanium detector. Let's move to the second part of my topic today. This is topic is devoted to neutron detection. And neutron detection is more complicated compared to gamma ray spectroscopy, specifically neutron spectroscopy is harder because neutrons are particles that are not so, as I mentioned, they have this feature that their probability cross-section interaction strongly depends on energy. This is why it's very difficult to detect them with conventional detectors, and you have to use these sort of detectors, which basically consist of two types: the so-called radiator. Basically, in the neutron detector should be some material which converts electron into other particles which can ionize the matter. And the detector itself, in some cases you have some external converters in the detector. In some cases you have the converter material inside the detector. I will show you the examples. In order to detect them, the material which is used as a converter should have a high cross section. That's the first thing, and the second, as the capture of it's in many applications, it's very important to distinguish between neutrons and gamma rays. And this material and all detectors of this type have to be quite competitive in order to suppress gamma rays and distinguish between neutrons and gamma rays. So in my previous lectures, I showed you some reactions which lead to creation of how neutrons interact with matter. And some of these reactions can be exploited in order to detect neutrons. And usually, as you remember, we differentiate between neutrons. We consider thermal neutrons, slow neutrons, and fast neutrons. And here I will describe you how to detect a thermal neutron. Usually, we have some target nucleus, and neutron hits it, interacts with, and creates nuclear recoils, for example, or alpha particles, or fission fragments. These charged particles that can ionize the matter lose their energy, and in reality create these pulse, create this pulse, which is also looks like Gaussian, and this average, the average of these distributions rarely shows you the move or energy value of the reaction. And this can be done by measuring the energy which is deposited in the detector. So I remind you about reactions which are used to detect neutrons. here we are talking only about right now thermal neutrons. The first one is neutrons plus helium-3, and this reaction leads to two charged particles, triton and proton, and release of about 0.7 MeV of energy, distributed between these two nuclear coils. The second reaction is neutron plus lithium-6. You have alpha particles and tritium, and this value of about 5 MeV of energy. Neutron plus boron. Boron also absorbs neutron very well, and you have lithium and helium particles. And energy also can lead, this reaction also can lead to the excited state of lithium. This about 7% of this reaction. One more reaction, gadolinium. This is reaction leads to gamma ray superconduction electrons. Gadolinium 155, gadolinium 157, and the last two reactions, fission reactions, where we have fission fragments with energies of about 116 deposited as just distributed between these fission fragments. Here the cross section, neutron energy, just a reminder how the probability of interaction depends on the energy of neutron. For these neutrons were located somewhere here, here. As thermal neutrons. This is for cross sections, for example, for fission or for helium. So let's talk about helium-3. All these reactions in reality are used to detect neutrons. And the first and one of the simplest detectors, which I use for detecting helium, for detecting neutrons, are helium proportional counters. Here the picture. This detector looks like a typical proportional counter, which I in detail described in my second lecture. It has a cylindrical geometry. Remember, cathode is the outer surface of the cylinder, and a thin metal wire is located inside the cylinder and serves as the anode. And during the interaction, neutron is absorbed, and you have two nuclear coils, nuclear charged particles, triton and tritium, with energy of about 800 keV, and energy between these two products is distributed according to their masses, according to these simple kinematic equations. And the cross section is pretty high by status almost 5,000 barns. And these two particles are moving in opposite directions and lose their energy through the ionization process and create electrons along the track. And all these electrons, like the typical counter, drift towards the anode and create an avalanche. And this avalanche gives rise to an electric signal, which is processed and can be measured. The amplitude of this signal, which corresponds to the energy of this nuclear coils. The second type of boron, of this type of detectors, are based on boron 10, which also effectively absorbs neutrons. And the main advantage of this reaction, you have here less cross section compared to helium, but you have more energetic recoils with total energy of about 2.5 MeV, which is also deposited in the detector. For these purposes, there are several types of detectors. Sometimes they can be used a gas, which is called barium fluoride, perfluoride, which is used in proportional counters, and I just put this picture today because we visited this morning Chkaltaya laboratory, and I saw their neutron detectors of this type, and I found this picture on the internet, and these detectors were invented in Canada in Chalk River laboratory. They're pretty high because they have to detect neutrons from the cosmic rays, and these detectors, as I understand, are used for cosmic rays physics even until now. It's very impressive. And there are other ways to use boron as a neutron absorber in proportional counters. Sometimes you can load scintillators with boron and can absorb neutrons there as well. Sometimes you even can have boron converters which are coupled to semiconductor detectors. There are different ways to utilize boron, boron-10, and in many applications we employed enriched boron-10 up to 90, even more, 95%, in order to increase the efficiency of detecting neutrons with this type of detectors. In other experiments, the second way of using boron in proportional counters is not directly to distribute it in the material or in gas, like in boron perfluoride detectors. You can coat the wall of your detector, the inner side of your detector, with this boron material, and you can use the mixture, for example, of typical proportional counter like argon CO2, and also detect neutrons. But in this case, you have one problem, that then you put and coat boron on the surface. You have two recoils that move in different directions, and if the interactions happens somewhere inside the detector, you can detect two particles and measure all the energy which is deposited in the detector. But in this case, there are a high chance, and it always happens, that your alpha particle or lithium ion are moving in the opposite direction, and one of these particles will be absorbed on the wall, and you will get no signal. You will always get only 1.747 or 0.84 MeV in this case, and you'll get this picture. Idealized picture of your energy spectrum of neutrons. Response function of your detector. Lithium also is used, but lithium, it's impossible to use this material inside proportional counters because it's exists only in solid state, And there are some ways to exploit it. For example, to add lithium instantaneator, and lithium, and of course lithium enriched to lithium 6. In this case, you can get some sort of scintillators, for example, lithium iodide doped with europium, which has pretty high light yield compared to sodium iodide. Sometimes, for instance, dope glasses with lithium, and this allows you also to detect neutrons. The main advantage of lithium is that you have higher energy, about 4.7 eV, but the cross section is low. But you have to also always find a compromise to between the cross section and the energy. It depends on your application. If the energy is high, it's easier to distinguish between neutrons and gamma rays. Sometimes this is more important, even if you want to get, you have to sacrifice your efficiency. Lithium also can be used in some liquid solutions with concentrations about 0.050%. Here is just an example. The lithium glass is connected to a PMT. You can use it as a simple scintillator to detect, only to specifically detect neutrons. Gadolinium-based detectors, they are not so frequently used, despite the fact that the cross section by Newton standards is pretty high. You can see the figure here by 3 order of magnitude higher than compared to 2 orders of magnitude higher compared to standard helium and boron counters. It was exploited in large experiments, for example, looking for neutrinos when you dope your liquid scintillator with gadolinium, and this gadolinium can effectively capture these neutrons and give rise to conversion electrons. And this conversion electron with a small energy, about 72 keV, is used to trace these neutrons. Also, there are some disadvantages of using gadolinium, that we have very strong gamma ray background and have to somehow suppress it, distinguish with neutrons and gamma rays. And here, the last reaction, which I showed you, and this reaction also can be used to detect neutrons. And this reaction is similar to the reaction that actually happens both in the nuclear reactor core. A typical fission reaction that we have fissile isotope, for example, uranium-235, and in order to detect your neutron, you have to construct the detector. It can be even an ionization chamber, and you coat the plate of your detector with this material. Neutron interacts with uranium and creates a couple of neutrons and fission fragments, typical fission reaction. And these fission fragments, they are charged and can ionize matter. And the energy of these fragments, the total energy is 160 MeV. If you have 2 fragments, you have to divide by 2, you can get 80 MeV. And you have 80 MeV of deposited energy per particle. Compare, for example, to 2.8 MeV in comparison, for example, with boron reactions. And this allows you to get a significant large amount of ionized electrons in your detector. And that's one of the best ways of utilizing these devices to monitor the nuclear reactor, the flux of neutrons inside and outside the nuclear reactor, which I will tell you tomorrow. And these detectors are very important for these applications. The main advantage of them that they don't need even a proportional amplification and can be used in a simple ion chamber mode without internal avalanche amplification due to the fact that the energy of this vision fragments is quite high compared to other neutron detectors. And I think for today it will be my last slide. And here I would like to say that in order to detect fast neutrons, it's more complicated task, I would say, because for thermal neutrons, you have a solid value of cross section, you have well-known material, you have a neutron, it interacts and gives you the signal. But when you have a distribution of energy of neutrons, and you want to measure them, you have to apply different techniques. Of course, you can use these conventional materials, but the cross section of these materials for fast neutrons is very low, and these reactions are used very rarely for measuring the energy of fast neutrons. And there are several types of detectors for this task. One of them is called simply in reality, this is scintillation detectors, liquid scintillation detectors, and the reaction is based on scattering, elastic scattering of neutrons of the scintillation protons, scintillation materials, which can give rise to proton recoils in the detector, and you can measure. You have a quite sophisticated, simple system. You can measure the angles of how neutrons scatter. You can understand the initial energy of the neutron and get your energy distribution. And in some cases, we use methods that allows you firstly to moderate and to make it slower, to make it thermal, your fast neutron. You surround a conventional thermal neutron detector with some materials which serves as good moderators, for example, polyethylene. And these technique allows you also to detect and measure, detect fast neutrons. Some other reactions, but they're not frequently used as well. You can use them, but it's not so conventional. I think I can stop now, and tomorrow I will tell you about all areas, almost all areas where we can use different type of detectors in nuclear instrumentations, in medicine, in other fields of our human life. Thanks for your attention. If you have questions, I can answer them. If you won't have, I will answer them tomorrow. If they would be happy.
Ok, mañana vamos a finalizar todas las clases, van a empezar igual a la 1, pero van a ser solamente de 1 hora, por favor. en una foto de las clases, pues se coge una guía en realidad, y a partir de eso vamos a tomar el examen. Entonces, después van a preparar cada uno por su parte el tema avanzado y bueno, solo están de una hora, van a ser preguntas de opción múltiple, entonces, por favor, eso quería hacerles recuerdo. ¿Tienen alguna consulta? No, tampoco del tema porque no voy a poder responder. Bueno, gracias. Nos vemos y nos esperamos mañana entonces.